Welcome to part B of our chapter 4. This is part B. In part A, we looked at two types of reaction: precipitation reaction, acid-base neutralization, and also the Cass-Forming reaction. In part P, we will look at two types of reaction in section 4.4, redox reaction or reduction oxidation reaction. And also we will look at single replacement reaction. And before we wrap up chapter 4 in 4.6, we will look at the unit of concentration in 4.5. So far, these are the types of reaction. You should make your own notes. Precipitation reaction, we covered that before in part A. Acid-base neutralization and Cass-Forming reaction that involve reaction of acids with carbonates and bicarbonate. And we will pick up from 4.4 redox reaction, and we will also look at the single replacement before we dive into unit of concentration and solution stoichiometry in section 4.6. So on my PowerPoint slide here, before we look in details on the oxidation reduction, I want to define the word redox. Redox is an abbreviation for two types of reaction, reduction and oxidation. Redox reaction is a reaction which involves transfer of electrons, and what we know, electrons are negatively charged. Remember, electrons are negatively charged. That will be a key critical thing you need to remember. I'm going to, by end of this subsection, I'll have covered or explained to you the 6 terms you should keep in your fingertips. You will see in the exam the definition of oxidation, definition of reduction, and in a chemical reaction, in a redox reaction, you should know what is being reduced, what is being oxidized. And also, you'll see questions on identifying reducing agent and oxidizing agent. I've listed 6 key terms you need to understand, you should be able to explain. So let's get started with the oxidation. Oxidation is defined as loss of electrons, right? It's a reaction where a species loses an electron or electrons. How do you know that a species has lost an electron? For example, sodium is neutral, but if it loses one electron, it becomes positively charged, all right? Positively charged. This is oxidation reaction. Calcium is neutral, but losing 2 electrons, Ca2 positive plus 2 electrons. Those numbers 2 and 1 are based on the group number, but the point here is when a species, an element loses 1 or more electron, they become positively charged. These 2 types of reaction represent oxidation, loss of what? Loss of electron. Now, reduction here, reduction is gain of electrons, right? How do you know that a species has gained electron? Remember, electrons are negatively charged. So chlorine, for example, is neutral, all right? If it gain an electron, or rather adding an electron plus 1 electron become negatively charged, just to give you an example on how to identify reduction reaction. If a species have an overall charge of negative element, no, that is a redox reaction. On the PowerPoint slide here, this is just an illustration on redox reaction where oxygen, initially the term oxidation meant addition of oxygen, all right, to form an oxide. And here is calcium, right, reacting with oxygen to form calcium oxide addition. Later on, we'll look at what is being oxidized and what is being reduced. I'll explain to you what those terms mean, all right? Once we get to an example, I'll show you how to identify the reducing agent, how to identify the oxidizing agent, because you'll be given those questions in the exam. So here, you should know the definition of oxidation, loss of electron, and reduction is gain of electron. You can use, I've seen some text using this acronym to oil, all right? And then this is oxidation is loss of electron, oil, and then here rig, all right, oil rig for reduction is gain of electrons, right? Gain of an electron or electron. That's how you can commit to your memory the two terms here. You should be able to divide those among the 6 terms I gave you, right? We'll go one by one. Now, it's important to note that these two types of reaction does not occur or take place by as an individual, but they occur simultaneously. One species is losing an electron, the other one is gaining an electron. For example, in the formation of sodium chloride, an electron is transferred from sodium to chlorine. An electron is transferred. You see the arrow to form Na positive and Cl negative, and the strong electrostatic force forms sodium chloride. So there is transfer of electron. Here we have a redox reaction in the sense that sodium is losing 1 electron, oxidation, and chlorine is gaining, reduction reaction. So one cannot occur without the other. The reaction is often referred to as redox, two of them. Now, in order to classify a reaction as a redox, we need to understand what we call oxidation numbers. This is a bookkeeping system used to tell or classify or identify whether the reaction is redox, all right, based on change in oxidation numbers. And what are oxidation numbers? Oxidation numbers just are arbitrary numbers assigned to an element. We'll see the criteria by which we do that. Oxidation numbers are used to determine if oxidation reduction reaction has occurred. We assign what we call oxidation number to each element in a neutral compound or charge entity. Charge entity could be polyatomic ion, all right? Charge entity here could be polyatomic ion. It could be an element such as sodium. This is an element. It could be a it could be monoatomic. This is an ion, or carbonate like that. This is polyatomic ion. We'll see how to, this is a charged entity. Carbonate is a charged entity, neutral compound, all right, such as sodium. So let's see, how do we assign oxidation numbers? Here are the rules, and I guess with practice you need to reproduce these rules, but it will help you in assigning oxidation numbers to either an element or an element in a compound or polyatomic ion. Let's go one by one. There are about 4 of them. One is an atom in their elemental state. Atoms in their elemental state form an oxidation number of 0. What do we mean by elemental? If it's just by an element, it's neutral, that's just gonna be 0. If it is copper, this is just gonna be 0. It is just by itself, it's nothing, it's just an element, elemental from the word elements on the periodic table. So if you are given an element on the periodic table, you should know that it has an oxidation state of 1. Now, oxidation state or oxidation number for monoatomic ion is the same as the charge. What do we mean by monoatomic? That means it is 1. Sodium positive, this is a cation. This has +1. There is calcium. This is +2. Depending on the group number, of course, this is +3. You should know from the periodic table how to predict the ionic charges. O2 negative, this has a charge of -2. Fluorine or fluoride, it's got a charge of -1 and so forth. Phosphorus is a charge of -3. So oxidation state or oxidation number, the same thing. Oxidation state or oxidation number for monoatomic is the same as the charge on what? On the ion. Ion 3, for example, has an oxidation state of +1. Rule number 2. Now, rule number 3, you got to be careful when handling oxygen. Non-metals usually have negative oxidation numbers, and these depend on the group number. Non-metals, remember, non-metals, oxide, sulfide, nitride, phosphide. Just to give you a few examples, iodide, fluoride, they have oxidation state of corresponding to the charge. Although sometimes, such as oxygen, when it is in peroxide, it can have positive or -1. You know, peroxide is, this is the charge of peroxide. Which means each oxygen has a charge of -1. Therefore, we say that in peroxide, we have -1. Hydrogen peroxide, this is hydrogen peroxide, right? Hydrogen oxygen has a -1, hydrogen has +1. We'll see later on how to calculate or determine the oxidation number. But remember, when dealing with peroxide, oxygen is always -1. Fluorine, another halogen, usually have -1, okay? They have -1. Rule number 4 here, the sum of oxidation number in a neutral compound is always 0. What do we mean by neutral compound? Sodium chloride, this is a neutral compound. All right. H2O, this is a neutral compound. If we want to find the oxidation number, we do the math and we equate to 0. The sum of oxidation number is always 0. So in other words, we know this is +1 and this is -1. So if we have +1 -1, this is equals to 0. Here, 2 times +1 for hydrogen plus -2 for oxygen, we equate to 0. These numbers +1, remember when we say that when it's a compound, the oxidation state for chlorine -1, +1. These numbers based on the group number on the periodic table. +1 for each hydrogen times 2, and then oxygen. Remember, oxygen is in group 6, got a charge of -2. Therefore, we equate to 0 for neutral compound. However, for polyatomic ion, here polyatomic ion, all right, such as sulfate, for example, SO4 negative, it has an overall charge of -2. It's a polyatomic ion. The sum of the oxidation number in polyatomic ion is the charge on the ion. Always the second element take first priority in assigning the oxidation number, and then you assume the other one to be X because it can have more than one oxidation number, all right? Don't use the periodic table for the first element for polyatomic ion. The second one take first priority in the sense that I'll say this is X. For sulfur, let oxidation number for sulfur P X. Therefore, each oxygen has an oxidation, or we assign oxidation state of -2. Therefore, X for sulfur plus we have 4 oxygens times -2 for each oxygen equals to -2. -2 is coming from this overall charge. Remember here, overall charge for the polyatomic ion, which means X, all right, X minus 8 equals to -2, which means X equals to +6. This is what you need to remember. Therefore, oxygen has a charge of oxidation state of -2. Sulfur has an oxidation state of +6. This is how you handle polyatomic ion. Suppose it has a positive, let's say NH for positive, like that. Therefore, you say X, let X be oxidation number for nitrogen. So X plus, all right? This is X plus 4 times +1 for each hydrogen equals to +1. +1 because of the overall charge here, because of the overall charge. So X, all right, plus 4 equals to +1. X minus, so this will be, in this case, it's gonna be negative, this is gonna be negative. We're gonna have this as negative. This will be -1 when it's like that, -1. This is -4 here. So this is going to be -4 equals -1. Therefore, X equals to plus what? This is plus 5. X plus 5. Always hydrogen, all right? When it is the first for hydrogen, take note, hydrogen, HCl, hydrogen equals to +1, oxygen, I mean chlorine here, chlorine, Cl equals to -1. This is when It's the first element. But if it is NH sodium hydride, sodium equals +1, hydrogen equals to -1. So it keeps on changing. Hydrogen has a unique, remember that, when to assign positive, when to assign negative. Therefore, I had to assign negative in ammonium ion, polyatomic cation, and then you do what? You equate to the overall charge, all right? You equate to the overall charge. With practice, this will help you out in determining the oxidation state, Let's see, there was supposed to be a question here for determining what was the question here. I want to make sure that we are on the right. What is the oxidation state? For this question, something is amiss here. Let's see if I can get here. Seems that we missed the question, but nevertheless, all right, I will write the question on my whiteboard. The question is, what is the oxidation, all right? The question for the multiple choice you see is, what is the oxidation, all right, a number of nitrogen. That is the question. Nitrogen in nitric what? Nitric acid. Nitric acid. And you know nitric acid is HNO3. This is a neutral molecule. This is a neutral molecule. So the first, always when you have three elements, the last in the chemical formula, take first priority in assigning the oxidation number based on the rules we looked previously, as if it's a single element or in a compound, it corresponds to the charge. And then the first element, the middle one, is always assigned X. So in other words, hydrogen equals to +1, nitrogen equals to X, we don't know, and then oxygen equals to -2. -2, assigning the oxidation numbers. Since it's a neutral compound, we equate to 0. Therefore, X, or rather, 1 for hydrogen plus X for nitrogen plus, there are three oxygens. 3 oxygens equals to 0. X for nitrogen. Each oxygen has oxidation state of -2. We will have to multiply by 3 -2. That's what I have here. So 1 plus X minus 6 equals to 0. X minus 5 equals to 0. X equals to +5. This is the oxidation state. And remember, if you are asked for each element, this will be hydrogen equals to +1, nitrogen equals to +5, all right, and oxygen equals to -2. So the correct answer is, here is B. You have to do the mass equate to 0 for a neutral compound. So that's how you will do it. You will determine the oxidation state for element. Please look at the end of chapter problems and practice on determining oxidation state for element in a compound. You will see that in the quiz. All right, that's all for the oxidation state and determining the oxidation numbers. Let's see, in single replacement reaction, and I'm going to define the other two terms or identify the other two species in a chemical reaction, what is being oxidized and what is being reduced. In displacement reaction, and here we are talking about single, all right, single replacement reaction. When we say a single replacement reaction, it is of this type A plus PC. We look at this as this is a cation, this is a cation, this is an anion. It can be polyatomic ion, and they are competing for this anion. If A is stronger than B, then it will replace B to form this. Remember, this is a cation, that is an ion. This is a generic way of representing a single replacement, or we call it displacement. In displacement reaction, ions oxidize an element. Well, it's important to understand before we look at a specific example. I want to walk you through on how to read the activity series in order to come up with the correct balanced equation for single replacement reaction. You need to learn the activity series. Activity series is a list of few selected elements, few selected metals on the periodic table listed from the top being lithium and all the way at the bottom gold, AU. I will just bring this. If you look at this, this is what we call activity series. I'll give you in the, or I'll allow you to use in the quiz, in the exam, to answer question on single replacement reaction. This is lithium, cold. You see hydrogen, I'd say metals, but hydrogen is a non-metal. That's why it's highlighted here. Highlighted that. They are listed in what? Oxidation state. In other words, each one of them is losing two or one or more electron, positively charged. They are listed in oxidation state. This means lithium can easily lose its one electron. Gonna talk about valence electron down the line, but look at it as losing the one electron. Potassium, if they are losing, here is the ease of oxidation increase, which means lithium is the most reactive, you can say reactive, and it will give, all right, it will replace something in single replacement. Anything below lithium, lithium will replace in a compound. If you look at barium, it will replace anything below it, but anything above it will not. It will not replace potassium. It will not replace lithium in single replacement reaction. Okay. So the element above hydrogen will react with acids, produce hydrogen gas. Have highlighted hydrogen gas because hydrogen gas is diatomic. When we say hydrogen gas, it is diatomic. This is hydrogen gas, okay? So elements above hydrogen will produce hydrogen gas. Elements above will react with acid to produce hydrogen gas. What does this mean? If you have, let's say, we have an element above, okay, such as iron here. If we have iron, solid, plus HCl, aqueous. Specific example here for what? Iron, All right, I'm using specific example of iron here to illustrate how hydrogen gas is produced. Iron is above hydrogen on the activity series. Therefore, iron will replace. I don't want you to assume that it's gonna be iron, chloride plus hydrogen. This is wrong. What this happened, it can be iron 2 or iron 3. Let's go with iron 3, all right? So iron 3 is FeCl, it's iron 3, okay? Plus hydrogen gas. Remember, it's gonna be hydrogen gas. And then this is aqueous, hydrogen gas. Iron 3 is soluble, so it's aqueous. Hydrogen gas is diatomic. This will affect how you balance the equation. So if I have 3 here, or rather, if I have 2 here, that means 6 chlorines. If I have 6 here, I have 2 there, and I have 2 here. Does that? No, that means I need to have 3. Here is 3. This is 3. This will be, no, this will be 6 here. Let's say 6. I have 3 here. So 6 hydrogens, 6 hydrogens, 6 hydrogens. All right. 6 chlorine, I'm gonna put 2 here and put 2 there. So I was right the first time. The equation is balanced. The point here is anything above hydrogen will react with acid to produce hydrogen gas. And this is hydrogen gas here. This is hydrogen. Hydrogen gas. Reactive metal is oxidized. What is meant by oxidized? Oxidized here, this is what I promised to identify or show you. Oxidized means meant to lose electrons. And remember electron bookkeeping? A species will be positive if it loses electron. So here is increase in oxidation number. You know a species has been oxidized if the oxidation number increase. For example, here sodium is neutral, going to Na positive plus 1 electron. If you look at the oxidation, this is 0, this is plus 1. There is increase in oxidation number increase. We say sodium is what? Sodium is oxidized. Sodium is oxidized in this case. So a species or a reactive metal is oxidized. That means it's meant to do what? To lose electron. If we go back here, the oxidation state of iron is 0, but when it's get here, it is +3. You need to see that. This is +1, this is 0 here, this is -1, this is -1. You will see which species has been oxidized, which one has been reduced. The one with decrease in oxidation state here, reduced means after the reaction decrease in oxidation, what you know a species has been reduced if it has decrease in oxidation number, oxidation number. Here, iron, we say it is oxidized, and hydrogen is reduced. That means we add electron. It was +1. Hydrogen, hydrogen is +1 here, but it has ended up with what? 0. Remember, oxidation state for at elemental state is 0. Hydrogen move from +1 to neutral 0. Hydrogen is reduced, and ion from neutral 0 to +3 has been oxidized. It has been made to lose electron. So those are the two terms we have looked at. You should be able to identify in a redox reaction which one is oxidized and which one is reduced, So you'll know that there is a reduction when there is a decrease in what? Oxidation number. Now, there is what we call oxidizing agent, reducing agent, all right? Oxidizing, because you see these terms in the exam, oxidizing agent. How do you identify oxidizing agent? This is the species gaining what? Gaining electrons. The species gaining electron is oxidizing, the one making the other species to lose electron. Reducing agent, the one doing the reduction, this one keeps the species which keeps electron, it keeps electrons or electron, or you can say donate, whichever way you want to commit to your memory. It's fine with me so long as you identify the reducing agent, you identify the oxidizing agent. Let me go back to this example here and identify the oxidizing agent, reducing agent, okay? Ion is donating electrons, is losing. So this is reducing, all right? Reducing agent. That means it's doing the reduction, is donating the electron. How do you know that it has donated electron? It has moved from neutral 0 to +3. Remember, when something loses electrons, it becomes more positive. It has lost 3 electrons, and of course 2 ions will give a total of 6 electrons. Here, hydrogen is gaining electron. We say that it is oxidizing. So here is oxidizing agent, right? Note that chlorine didn't change, negative and negative, still negative. Each chlorine on the reactant side, on the product side, is the same. So those are the 6 terms you need to know. You should be able to define the oxidizing agent, the reducing agent, what is being oxidized, what is being reduced. And we looked at the oxidation and reduction previously. 6 terms you should commit to your memory. So elements higher on the activity series are more reactive. I explained that earlier on, so you need to know that takes this as ion, takes this as ion. So here is another question. There was a question, I believe, you are to answer here. Yes, I'm going to write again on my whiteboard what this question here was all about. Something is missing here. All right. The question is, does a reaction occur? All right. Here the question is, does reaction occur? All right. Occur when aqueous solution, when aqueous solution, all right, aqueous solution of nickel 2 chloride, NaICl2 chloride, and this is aqueous, is added, all right, added to a test tube containing all right, containing strips, all right, strips of metallic zinc, all right, metallic zinc. So in this case, you need to write the equation, and the equation is this. We are having zinc, which is solid, metallic is solid, plus nickel Cl2. Will the reaction take place? Of course, I don't expect you to memorize the activity series, all right? With this before you in the exam, in the quiz, you have to look at the position of zinc with respect to nickel. Zinc is above nickel, which means it's more powerful. It will replace, zinc will replace nickel. And remember, it's +2, all right? So if it's +2, the reaction here, or the product, will be zinc chloride plus nickel. The equation is balanced the way it is. This is solid right here. Nickel to chloride will react. And the question here was, will it react? The question was this, and the answer is yes. So A is yes. And it's just illustrate how to use the what? How to use the activity series. Please download this activity series, use in your homework assignment, learn to use in your homework assignment. I'll allow you to use in your exam. Please make sure you know how to read the activity series and how you predict the chemical, predict whether the chemical reaction will take place. If yes, you should be able to balance the equation. Remember, acids react with, all right, active metals. Anything above hydrogen on the activity series will react with acid to produce hydrogen gas, and hydrogen gas is diatomic. Let's move on to section 5.5, and this is the unit of concentration, all right? I think, let's see here, before we move on that, sorry about that. Let's see an example here, okay? Which element is reduced and which element is oxidized in the following reaction? Okay, how will you know? You have to assign oxidation numbers to each element on the chemical reaction. And anything, all right, to answer that question, it has to be a species on the reactant side. Let me just write the equation here. It is 3 moles of iron 3 nitrate, iron 3 nitrate. This is 2 aqueous here, plus 2 moles of Al. This is solid, going to 3 moles of iron, solid, plus 2 moles of what? 2 moles of aluminum nitrate. 3 there, 2, and this is aqueous. The question is, how do you identify reducing agent, or which element is reduced? That means the one we are adding electron into. Which element is oxidized? And maybe you'll be asked also on the other side, the reducing agent and oxidizing agent. I'm just going to use this to show you that. So we know from here, the oxidation number for iron is +2. We are just uncrossing. I'm just uncrossing that these two came from what? And then the nitrate, of course, will have -1. We don't have to assign each one of them. This is 0. Remember the oxidation state for elements are 0. Oxidation state at elemental state, they have 0. This will be 0. And then this will be +1. This will be +3. Sorry about that. This should be +3. Here we should have Ln. This is 3, not 2. Aluminum has 3 here. Take note of that. So this is 3. This will be +3. So if I look at what is happening on the reactant side and what is happening on the product side, sorry about that, iron is moving from what? +2 to +3. So this is reduced. And, all right, aluminum is going from 0 to +3 here. We say this is oxidized. Oxidized because there is increase in oxidation number. It is meant to lose, it's losing electron. Becoming positive means we are less by 3 electrons. Here we have added 2 electrons, and of course, the coefficient will balance out those. We say here, because you may be asked, therefore, iron is the oxidizing agent. What is being reduced is the oxidizing agent. What is being oxidized, so this is right here, iron or aluminum, Al is the reducing agent, because you may see in the quiz, in the homework assignment, you are given an equation and you are asked which one is being reduced, which one is being oxidized. Or it could be exact same question and you are asked which one is the reducing agent, which one is the oxidizing agent. I'll put more resources on the folder on Canvas. Please make sure you work those other resources on redox reaction, Let's shift gears to section 4.5, concentration of solution, all right? Concentration of solution. Concentration is basically the way chemists express relative amount of solute moles per given quantity of solution. That how many moles, for example, how many moles of solute in a given quantity of solution. We use concentration or molarity. Molarity, they are used interchangeably to express relative amount of moles per given quantity of solution, the quantity of solute. And remember, solute is what is present in small amount. In this case, we use the concentration to refer to molarity, and sometimes you may see molarity, or what is the concentration of the solution? What is the molarity? It's the same thing. Two terms used interchangeably, we call concentration or molarity. Molarity is a unit for expressing the concentration of solution. You have seen certainly in the lab, let's say 0.1 molar HCl or 1 molar HCl or 12.1 molar HCl. The numbers 0.11 and maybe two significant figures, 1.0 molar, it's just the numbers represent 1m, or you may have seen this M stand for molarity, which is a unit of expressing the concentration of solution. Using this example here, 12.1 is more concentrated. We have a high number of moles of HCl. This should be HCl right here. Okay, should be HCl right there. So remember molarity. If you see this molarity, we use M, uppercase M is simply unit of concentration. Unit of expressing concentration. And we use this molarity equals to number of moles of solute over volume, all right, volume in liters of solution. Sometimes just abbreviated that M is equals to number of moles over V, and then subscript L for volume in liters of solution. So remember, M, number of moles of solute, over volume in liters of solution. There are other equations you need to remember. It's not going to be one-stop shop that you are given the number of moles. The top part, if not given, you have to use this equation. Mass in grams, which you may be given over molar mass or atomic mass. This one use what? Use periodic. You have to use the periodic table if you are given. If you are not given, sorry, if you are not given, use the periodic table where mass is the given molar mass of that compound, so that you have the numerator, the top part, volume in liters of solution. There are some conversion factors you are expected to know, all right? If given the volume in ml, you need to change to liters. Recall, all right? 1 liter equals to 1,000 ml. You may not be given, but you are expected to recall this so that you convert the volume of, all right, volume of solution to liters. And then you plug it in the equation to get the what? Get the molarity. So we'll see that how to calculate that. Let's see, out of this equation, out of this main equation, you can generate two other equations here. Right here, between, this is equation 2, number of moles is given by the molarity times volume in liters, volume in liters. Okay. Volume in liters. Or this is equation 2. Volume in liters is given by number of what? Moles of solute over molarity. This is equation 3. I will not give you all the 3 equations. All you will be given in the exam. All right, I'll give you the formula sheet in the exam. Remember to manipulate the main equation. This is what you will only get. Okay, the rest you have to rearrange to derive the, or you should be able to derive the 2 other equations so that you answer in you use to answer the question. For example, here, let's see. Learning check, calculate the molarity of solution that contains 0.175 moles zinc chloride in exactly 150 ml. So I know, in case, so I know the molarity equals number of moles over volume in liters. So it is 0.15 liters. Therefore, molarity equals 0.175. So I didn't have to calculate the number of moles, right there over 0.150 liters. Here, let's see, if I divide that, it is 0.175 divided by 0.150, and I get, you'll see in the calculator 1.1666666666. This is more than what we need for our final answer, and especially if you are keying in on my level mastering, you should go with the significant figures. I see here, this has 2 significant figures, 3 significant figures. So let's go with 2 significant figures. This is 1, therefore 1.2 molar zinc chloride. So this is the molarity. We have to go or use two significant figures because of 2 significant figures here. All right, so that's how to use molarity equation to answer. Please always remember to change the volume to liters before you plug it in your in your questions. One thing I want to bring to your attention is we can either say 1.2 moles per liter is the same thing, or 1.2 with uppercase M is the same thing. it's the same thing. So next time you see moles per liter or uppercase M, it's the same thing. Let's see, B, how many milliliters of 6 molar NaOH is needed to provide 0.350 moles of NaOH, NaOH, all right? So what I'll do is, if you are given that, how many? So we are looking for volume. Volume in liters is given by number of moles, in this case, NaOH over molarity How do I do that? Remember, molarity equals to from. So if I multiply here by V in liters, multiply here by V in liters, I'll cancel that and cancel that, divide both sides by M, divide both sides by M. This is where I'm getting number of moles over molarity. That's rearranging the molarity equation. So plugging in there, number of moles is 0.350 moles over molarity, which is what? 6.00 and 3 significant figures. Why 6.00? Why not 6.0? And this is moles per liter. This will give us in liters. So if I plug that, 0.350 divided by 6. All right, so 0.350 divided by 6. I see I have 0.0583. And this is liter. So if it is ml, going to be 58.3 ml, 58.3 ml, just using the molarity. I'll recommend that you do more practice on, all right, you do more practice on using molarity equation. There will be more YouTube resources on how to use molarity equation to perform calculation. Either find the number of moles, either find the mass of a given solute using the molar mass. Again, periodic table will be handy in this case. Always remember to change the volume to liters. Let's look at another equation or another law used in determining the molarity of solution. And these all right, has to do with preparing solution using the volumetric flask. Mixing of solution. To create a solution of non-molarity, you weigh out mass, all right? You are asked to prepare a solution of sodium hydroxide, you will have to mass out and then put the flask. There is a demonstration in the text, all right? And what this means is just you weigh out, after doing the calculation on the desired molarity and how much you need to weigh out, you'll dissolve in a volumetric flask. This flask, they are more precise. The calibration, you may recall from the lab, that the calibration mark are always given along the neck here, that if you feel the solution to that calibration mark, you have exact volume. We have either 5, 10, 15, 20, 100, even up to 2 liters volumetric flask, up to 2 liters volumetric flask, okay? So that's how you prepare the solution of known concentration. Here is, let's look at one example on how you are required to mass out or prepare or determine the concentration given a mass of a solute. Calculate the molarity of a solution made by dissolving 5.00 grams of glucose. 5.00, that means your final answer will have 3 significant figures. Note, why not 5? Why not 5.0? Why not 5.0000? Fact that is, you should have 3 significant figures. Now, you need to find the molar mass of sucrose. Here, real quick, molar mass of sucrose is 180.156 grams per mole. Remember, molar mass, we use grams per mole. Insufficient water to make 100 grams. Okay. So here is convert the 5 grams, 5.00 grams of C6H12O6 times the molar mass, all right? Molar mass is 180.156 grams of sucrose, 6H12O6. This is 1 mole of C6H12O6. So that grams and grams. What I'm doing here is just changing the grams to moles. So 1.5 divided by 180.156. All right. This is 0.0278. These are moles of what? Moles of C6H12O6. These are number of moles. Remember to change the volume. 100 ml times 1 liter, 1,000 ml. I'm doing the conversion, so 0, this will be 0.1. 0.1 liter. Therefore, molarity equals number of moles of volume in liters, 0.027. If you look at that, 0.728. You know, in fact, I shouldn't have added that to product, but nevertheless, 0.278. All right, 0.078 m. This is molarity for sucrose. Molarity for sucrose. So remember that to change. Alternatively, some folks, I don't know, you need to learn. Some folks can start by saying, if I dissolve 5 grams in 100 ml, you change the moles, mass to grams. 1 mole over 180.15, 15 here, 6 times. You want to get rid of ml, so here is 1,000 ml for 1 liter, and grams will go, ml and ml will go. and then you'll remain with moles per liter. This is the same thing. You'll get, or you should get the same answer, 8 moles per liter, or 0.278 uppercase MOC 6H. Sucrose is 12 or 6. All right, get that? All right. So that's how you determine the molarity of solution. Do more practice on that. Let's shift gears to another method of determining the molarity of solution using dilution law. All right. Usually or routinely in the lab, we the solution or reagents are prepared in high concentration, yet in order to work comfortably in your workstation or perform an experiment, it needs to be diluted to bring down. We use what we call dilution law, all right? Dilution law is simply, you need to remember this equation, it's another method of finding molarity, bringing down a concentrated solution to lower concentration. This is common or common equation. I call it as dilution law. It is another way of determine, or another method of determining the molarity of solution is M1 V1 equals to M2 V2. On the PowerPoint slides, this means concentrated molarity of the concentrated solution, volume of the concentrated solution, molarity of the dilute solution, volume of the dilute solution. So remember that, okay? By reading the problem, you will have a sense of which one is the concentrated solution. For example, what is the final concentration of this and that, okay? An example here, how many milliliters of stock solution of 6 molar nitric acid will you have to prepare 110 ml of Z? So if I look at the initial concentration, this is more concentrated. This is less concentrated. So this is M1, this is V1. So if I look at that, I am given what? I'm given M1, which is 6.0. This is what I'm looking for, because how many ml of that is V1 will you need to prepare? 110, this is what is given. This is 110 ml, and this is 0.5. Yours is to rearrange the equation. Yours is to rearrange the equation. We have that, we have that. If you look at the identities I do have here, 1, 2, 3, 4, you have to rearrange in such a way that you know what you are looking for. For example, M1 is given by M2 V2 over V1. This is equation 1. M2 is given by M1 V1 over V2. Equation 3. Equation 4 could be for volume, or I mean 3 for volume. It's gonna be M1 V1 over M2. This is equation 3, and V1 is given by M2 V2 over M1. If you look at all these 4 equations, you generate from this equation. So if I'm looking at my numbers here, I'm looking for V1. I don't need to have all these equations here in order to pick one and say, I'm looking for V1. All I will be given, or I'll give you, is this. You'll only be given this in the exam. So if I know that, therefore, V1 equals to M2 V2 over M1, which is equals to, our M2 is 0.5 and 3 significant figures. It's gonna be our 3 significant figures times V2 is 110 ml over what? Over M1 here is 6.0. It looks like two significant figures. We have two significant figures here, two significant, so our final answer will be two significant, M and M. So if I plug in my calculator, all right, 0.5 times 110, all right, divided by 6, all right. I see it's 9.1666667 ml. I don't need, or we don't need all these digits. We need to round off to the correct number of significant figures. I see we have two. This is 9.2 ml. Always check what? Always check the significant figures. We had 2 here, so division. That is the dilution law. Please work on more problems at the end of the chapter problems. Odd numbered, I think they are red numbered problems at the end of the chapter problems has solution in the pack, okay? Just so that you get more problems on that. Lastly, what I want to look at is in chapter 4, this is the last item I want us to real quick go through, is the solution stoichiometry. Remember, in chapter 3, we look at the stoichiometric calculation, moles to moles, moles to mass, and mass to moles, or mass to mass. But here, we are extending the stoichiometric calculation to the volume, that we will use volume this time round, right? Look at the titration and how the stoichiometry is used in determining the molarity of solution or the number of moles of solution. This concept will transcend Chem 1. You'll also need in Chem 2, you'll also need in analytical and even organic solution stoichiometry. We'll need to balance the equation, understand what those coefficients in the balanced equation mean. This part here, mass of solid A to moles of solid A, we use molar mass to do the conversion. We looked at that. And moles of A to moles of B coefficient in the balanced equation. This is chapter 3 concept. This is chapter 3 stuff. But here, this is where the solution stoichiometry comes in, that the molarity of solution containing substance B, molarity. That means there should be a volume somewhere. Use the volume of solution containing B, find the number of moles, move on to that. This is just a roadmap. With practice, you don't need to memorize the roadmap given on the PowerPoint slide. It's just a question of practice, okay? Let's see, for example, here, what I recommend is writing the balanced equation, and I've seen it being effective, writing the balanced equation and writing the information below each reactant, each product. Make sure the equation in solution stoichiometry. Write a balanced equation, write the information below each reactant so that you can determine what is being asked. For example, here, how many grams of sodium hydroxide are needed to neutralize 20 ml of 0.150 molar sulfuric acid? If I look at the number of significant figures here, we have 3. We have 3 here. That means the final answer should have 3 significant figures. So here is the reaction, okay? We have sodium hydroxide. We're looking for mass. How many grams? Okay, it's got to be aqueous. We're going to convert to grams. Sulfuric acid. This is acid-base neutralization, which means an acid react with a base to produce a salt. In this case, Na2SO4, sodium sulfate. Remember the crossover rule, you should know, aqueous plus liquid H2O plus liquid H2O. So we add that. Make sure that the equation is balanced. Otherwise, you will not arrive at the correct conclusion. 2 sodium so as to balance the 2 sodium here. So we need to put that in front of sodium hydroxide to balance the sodiums. Let's see oxygen. 2 times 1, 2 oxygen plus 4 is 6 oxygen. So here is 4. I have 1 here. I may need a 2 in front of H2O so that we have here what? 2 oxygens plus 2 is 6. 4 plus 2 is 6. So oxygen is taken care of. Let's see hydrogens. 2 times 1 is 2 plus 2 is 4. 2 times 2 is 4. So the way it is, oxygen, or I mean the coefficient in the balanced equation, we need that. We're gonna need that in our calculation. So the information we have, this is what I was saying, you need to write below each species to neutralize 20 ml. What I know here is we have 20 ml, which is 0.0 to 0 liters. Always change the volume to liters because of molarity. What do we know? Molarity is, this is volume. Molarity equals 0. What? 0.150 mole, which means the number of moles is molarity times volume in liters, which is given by what? 0.150. That's the molarity times 0.020 liters. Let's see. The number of moles here, I'm just going to find out the number of moles. So it's 0.150 times 0.020. All right, 0.150 times 0.020. I see here 0.003 moles. So I know how many moles of sulfuric acid are in 20 ml, and I had to change the liters because of what? Because of the units of molarity, moles per what? Moles per liter. So we use the mole ratio to try to fill in this portion for reagent 1. We know for reagent 2, this is the volume, this is the molarity, this is the number of moles. And what we use is the mole ratio. This does not mean we will have 0.04. No. This does not mean we'll have 0.3 molar. No. The only mole ratio, this is all what we know from the balanced equation, from the coefficient. These are the mole ratio in this reaction. So the only thing we will relate is the number of moles, which is 0.006. All right, here. I'm just going to draw a parallel here so that you don't get confused. 0.006, because it is 2 to 1. So if I know here, this I'll just multiply by 2. In fact, that is all we need for what? to answer the question, how many grams? So this is a standalone number of moles of NaOH is given by the mass of NaOH over molar mass of NaOH, which means mass in grams is given by molar mass mm times number of moles. This is given by number of moles here is 0.006 moles times 40. Let's just approximate that 40.0 grams over mole. So when I multiply by that, all right, 0.006 times 40, I have 0.240 grams of NaOH. This is the grams of NaOH needed to neutralize 20.0 moles of grams. So here is an example. This is a standalone, okay? There are two equations for finding the number of moles. Look at the information given, asking yourself if it makes sense to use. You cannot use the molarity equation to find the number of moles because here we don't have the volume. So that's what I wanted to show you. Please, if I go back here, have the information for one reagent, the other information for one reagent, and reconcile with the question and see if you are in a position to plug in the information, use the right formulas, and end up with that. So this is the answer for the previous learning check. Now, let's see, look at the solutions document in titration. Titration is an analytical technique in which one calculates the concentration of the solute in another solution. So in titration, this is a stopcock, this is a purette. And what goes in the purette is what under purette is analyte, what you are analyzing. What goes here is called the standard solution. This has known concentration. We know the concentration. That's why we don't know concentration. Unknown what? Unknown concentration. So in titration, we add an analyte, probably maybe blow up this so that you understand how titration is performed in the lab. You will perform this in the lab for those who are taking the course right now. We don't know the concentration of the analyte, but we know the volume. An organic dye indicator, in this case, acid-base indicator, is an organic molecule which changes color at a specific pH, all right? This indicates or will show the endpoint. A special equipment called purette is used to add or to contain the titran, what we're using to titrate our analyte. You add at an increment the titran until there is a color change. This indicator here changes color at some point, which signifies the equivalent point. There are terms you need to remember. You need to define titration, of course, which is analytical method by which chemists use to determine the molarity or concentration of a solution. And then equivalent here, equivalent it is a point in titration, equivalent point here. Let's see, equivalent point. It is a point in titration where the number of moles of the titran, that means from the puree, which has gone into the flask, is equal to the number of moles of the analyte at equivalent point. It is a theoretical what? It is a theoretical point. Before we come to this, let's understand the equivalent point. It is a theoretical or a point in titration where there is a equal number of moles of the titran. What goes in the puree is the titran or standard, and what? And the analyte, what we are analyzing. At this point, there is the color change of solution signifying the equivalent point. We call that endpoint. Endpoint, all right? The reaction is complete at equivalent, which is based on the endpoint. Endpoint is a point in titration where there is just color change, all right? It's time to stop the titration. Here's the roadmap you can follow for titration problems. It's the same thing. Let's see an example here, please. Key terms. Equivalent point, you should be able to define that. What is the standard? What is the analyte? And the endpoint for that. Let's see on the PowerPoint slide, how many liters of 0.1 no 0.500 molar HCl are needed to react completely with 0.100 molar lead to nitrate to form a precipitate. Just like before, we balance the equation. So what do we know? Lead to nitrate, PPO3 with a 2. This is aqueous plus HCl aqueous to produce a precipitate, PPCl2, solid plus, this is going to be to form a precipitate, HCl and double H2 NO3. It's just gonna form a precipitate. The point here is, let's see, in titration, is the equation balanced first of all? No, we need to balance the equation, which means we need a 2 there. We need a 2 there. There is a 1, there is a 1. So below each reagent, we write the information given. What we know for HCl 0.500 molar. This is the molarity of HCl. What we know here is number of moles is 0.100. That's all the information we are given. So if I want to use the mole ratio in the balanced equation here for everything I know for lead, I should know in terms of 1 to 2. So here the number of moles, 0.200 moles. You see that? We know the number of moles of layer 2. This is number of moles of layer 2 here, which means for complete reaction 1 to 2, for every one here consumed, 2 of that consumed. To completely precipitate this number of moles, we need 0.2 moles of HCl. Remember here how many liters. So volume of HCl needed is volume in liters is given by number of moles over molarity, which is given by 0 0.0, 0 point, no, 0 0.2, 0 0.2 0 moles of 0.500 moles per liter. Moles and moles will go, and we have volume in liters. So 0.2 divided by 0.500. Okay, I have here 4. No, it's 0.4. It's gonna be 0.4. This is 0.4 liters. So how many liters? Yes, we are looking for liters, not ml. All right. The question is how many liters? So we have just to go with the volume in liters. Volume in liters. We have used the titration. It's the same thing, solution stoichiometry. Remember, I'm using here the mole ratio. Always balance the equation. They will not tell you to balance the equation. You are expected to know that always balance the equation. Something we learn in chapter 3. We learned that in chapter 3, and always write the information below each reagent. You can't go wrong with that. Remember how to interpret a chemical equation. Let's see another example on the learning check. What volume of 0.128 molar HCl is needed to neutralize 2.8, all right, 2.8 7 grams of 7 grams of what? 7 grams of magnesium hydroxide. Magnesium hydroxide. With this, you need to write the balanced equation, all right? Between HCl, so let's say magnesium hydroxide plus HCl to form magnesium chloride. Remember to write the correct formula for your compounds using the crossover rule. MgCl2 plus H2O plus H2O. Balance the equation. So here, if I put a 2 in front of HCl, that will balance out the what? That will balance out the hydrogens to hydrogen. So the equation is balanced. So here is 1, here is 1, all right? And this is liquid H2O. The equation is balanced the way it is. So what we know is the mass of magnesium hydroxide, and molar mass of MgOH 2 is 58.319 grams per mole. This is the molar mass of magnesium hydroxide. Therefore, number of moles, look here, number of moles of MgOH 2 is 2.87 grams of MgOH. That using the molar mass as a conversion factor, 1 mole of MgOH like that to over what? Over 58.319. This is grams of MgOH. Or to like that. This will go away, that will go away. And I have here 0.0492 moles. So this is the number of moles of magnesium hydroxide we have in 2.87. So with that, I know the moles of magnesium hydroxide 0.0492. And then times 2, if I have that, number of moles of HCl is 0.0984 moles. I'm writing all the information below each reagent. How do I know? I had to convert this number of moles. Mole ratio is 1 to 2. Therefore, to consume 0.04192 moles, we need 0.0984 moles of HCl. What volume of 0? So I know molarity. Look at this. Molarity equals to what? 0.128. Remember, we are almost getting there. We know the molarity. We know the number of moles. Look, we know the molarity. We know the number of moles. Therefore, volume, and remember volume in liters is given by number of moles. This is volume of HCl, by the way. Number of moles of molarity, which is equals to what? 0.984 over moles of 0.128. Remember, this is moles per liter, so that moles and moles will co. Moles and moles will co. So if I divide that, all right, it's going to be 0.0984 divided by 0.128. I have, this is the same as 0.7669 liters. This is volume in liters. But if we want to change to ml, all right, if we want to change to ml, this will be 0.769 ml of HCl. So to recap that, always write the balanced equation in titration solution stoichiometry. Always make sure you balance the equation. Remember, it was solution stoichiometry, and in stoichiometry, balance the equation. What are the coefficients in the balanced equation? It's the mole ratio. So you have seen me comparing the number of moles and number of moles. I'm not comparing molarity and molarity. I'm not comparing what? Volume and volume. It's always the number of moles, always the number of moles. With that, that marks the end of part B of chapter 4, reaction in aqueous solution. Please practice, practice, practice until you get it. See you again in chapter 5. Thank you.